let me do this in an example and see if that's. So I start with x1100, and that's the point class. Or rather, it's the point itself. Now it's the point class. Okay. If I partial 1 or partial 3 this guy, it dies. Because I got an 11 there or 0 there. Only if I partial 2 it will something happen. It'll become 0, 1, 0, 1, 0, 1, 0. The 10 will become a 0, 1. If I partial 2 that, it'll die. If I partial 1 it, I'll get x 0, 1, 1, 0. If I partial 3 it, I'll get x 1, 0, 0, 1. And then I could partial 3 this one, or partial 1 that, and get to x 0, 1, 0, 1. And then I can partial 2 that and get to x 0, 0, 1, 1. Okay. So there are the 6 Schubert classes in GR24. What I want to do now is improve these operators, these partial i's, or partial alphas. I want to improve them to some new operators that don't square to 0 like these guys do, but they square to 1. So let's replace partial alpha by, so okay, if they're going to square to 1, they had better be degree 0 operators. Well, if they're going to be homogeneous operators, so this guy was a homogeneous operator with degree -1. That these have the same degree, and then we divided by this, and so the degree went down by 1. Or if you're thinking in cohomology, the degree went down by, so the length went down by 1. The number of inversions here went down by 1 each time, and I killed an inversion. The degree as a cohomology class went down by 2, because the dimension of the complex numbers of the reals is 2. So if I say something is confusing about those 1 versus 2, you should call me on it. I'll try to stick to cohomological degrees. So each time these partials were homogeneous with degree -2. Now I want something that's homogeneous with degree 0, so that it'll square to the identity. So I'm going to need, in that case, to soup this up with some new parameter that I'll call h bar for some reason. That will be homogeneous to degree 2. Now we've met things that are homogeneous to degree 2 naturally so far in this. All of the yi's, the equivariant parameters, were homogeneous to degree 2. So remember, they came from cohomology of CP infinity, which is a polynomial ring with 1 generator in degree 2. So I can do that. Now this thing is a degree 0, but it's still going to square to 0. So the great trick is to add the reflection to it. And this really tripped me up. I actually want to add negative reflection to it, just to match some conventions in the literature. So what happens now when you take this thing and you square it? Well, this guy squares to 1, and you get this h bar commutes with everything. R alpha, partial alpha, plus partial alpha, R alpha, and the same to minus there. And then this guy squared to 0. But this is 0 already. R alpha and partial alpha anti-commute. So this thing squares to 1. So one way in which, so the idea is going to be, we're going to start with the point class like we did, and instead of applying the partial alphas that we understand very well, we'll apply these operators, and we'll get something that that's like what we had before, but it's strictly better in the sense that we can recover the old classes by taking h bar to infinity, not to 0. If you take h bar to 0, then things become really easy. So with h bar being 0, all we're doing is taking this single point class and reflecting it around to other places on here, putting it over there, over there. It would be supported at just one point if you take h bar to 0. So it's h bar to infinity that we should recover, this term dominating and the other term being stupid, and we need to keep track of what power of h bar we're interested in, but we'll recover the old story. So that's the sense in which this is strictly better. Okay, so let me define the Malakakunkov class is MO lambda. And again, lambda would be running over n choose k. So the first one, MO of all ones, then all zeros, that's going to be, and at some point I'm going to want these to be classes of something. So I'm going to put brackets here with the version of this without brackets to be named later, okay? So there will be some geometric object later that will have a cohomology class that will be these, but don't worry about that yet. So I'm going to define this as just the same Schubert class I had before. So this is that point class. That's where we get started. Now, what we did before was to take this class and apply these divided difference operators and created all the other Schubert classes. So geometrically, what happened was we started with a point in here, and we swept it with these minimal parabolics, and it got bigger and bigger and kept making Schubert varieties. So now I want to do something like that, but instead of using the partials, I use these. So I define MO lambda to be, well, so I'll just say this as a recurrence, and the recurrence will clearly make a definition. MO lambda should be MO lambda with positions I plus 1 switched, where I'm going to apply minus Ri plus H bar partial I. So this is enough to make the MO lambdas unique. So next you want to be sure they exist. If you have a particular lambda, there's a bunch of ways you might make lambda starting from here, right? You might do switches in different places, bounce things around, and you want to know that no matter how you get them to the positions lambda where you want them, you get the same answer. So you need to check that faraway switches commute, that if I and j are further than 1, these operators commute. That's pretty easy. You need to check that if they're adjacent, if j is I plus 1, then they satisfy the grade relation, and that's boring, but checkable. And you need to check that this guy squares to 1, which I did, and that's good enough. So that tells you that these classes exist, whatever they are. They have this weird new thing, h bar, and we're going to talk about before. I'd like to point out how different this story is than this one. Here we had cases. We could only go in one direction. And once we went in that direction, we tried to go in that direction again, it would die. Here, we don't have cases. If you want to do it twice, that's fine. You'll get back to where you started, because this guy squares to 1. So I think this is a strictly more beautiful construction. You could take h bar to infinity here. So what's going on? I'm not saying that if you take one of these MO guys, which seems to be some polynomial in h bar with Schubert class coefficients, I'm not saying that if you take h bar to infinity, you get the Schubert classes on the nose. You get them times h bar to a predictable power. If you divide by that predictable power and then take limits, okay, then you'll get the Schubert classes on the nose. And it will kill the thing that would have gone over here. So that's how this 0 is hiding in this once you bring in the expected powers of h bar. Questions right now? Yeah.
Just thinking in this diagram, wouldn't this first one, wouldn't we don't get any new cells or any new classes or anything?
Well, I mean, like, let's start here, where the thing we had before. Let's apply this first operator. So if I apply the partial, I'll get this. And if I apply R alpha plus H bar partial alpha, I won't get this, I'll get something else. I mean, why don't we do it right here?
Okay.
Why don't we do it right here? So I'm going to, from here to here, I applied this partial left, okay? But now instead I'm going to apply R left minus that plus H bar partial left. And so I should get this thing, so, and all these guys can be 0. Here I will get that, but also with this factor of H bar. So this is a product of 3 linear factors here. And at this end, I will get that minus this reflected. So this reflected would equate those ways, but it would equate these ways. So plus that. So this is just different from that. But if you take H bar to infinity and you divide by H bar, then this term will die, and you get that. Okay, so where are these? Well, 2 things I wanted to get into. Where are these classes living? Why do we have this extra factor of H bar? Yeah?
Can you explain again why for the term caused by R left is that one you know?
Yeah, so you take this guy and you apply the R and it flips to there. So instead of having these here, I'd have these here. Okay? But then I want to negate. Now this is a product, this thing is a product of 3 factors.
Okay.
So I can negate by negating one of them, and I negated that one. Not for any particularly good reason. I could just as well have written minus that. I mean, what is kind of nice is to notice that this is a common factor of them. All right. So, how come I have this extra factor of H bar? It's got the right degree to be an equivariant parameter. So I want to have some ring that's not the T-equivariant cohomology of the Grassmannian, but has this extra parameter. And the one we're going to use is we're going to take not the Grassmannian, but its cotangent bundle. And so the torus acts on the Grassmannian, so therefore it acts on the cotangent bundle symplectically. This is a symplectic manifold, and there's a natural way to extend the action. But there's a new circle action this guy has, which is you can dilate the fibers. So there's going to be an extra copy of C cross, and this is dilating the cotangent fibers. Now, it may seem silly to consider the cohomology of the cotangent bundle because cohomology is supposed to be homotopy invariant or T-equivariantly homotopy invariant, and the cotangent bundle retracts to the base. So this thing is isomorphic to the cotangent bundle to the base. And now things seem really stupid because this was acting by dilating the cotangent fibers, and we don't have those anymore, we just have the 0 section. So this is now acting trivially, in which case I don't really need to consider these together. I can separate this back. So this is now acting trivially. It wasn't acting trivially there. but now that I've gone with this homotopically equivalent space, it is. And so that I can rewrite as TF rank cohomology of the Grassmannian tensored over Z with H star C cross, the dilation rate cohomology of a point. So this is as a isomorphic as a ring. Okay, this is the sort of thing. If it were acting non-trivially, then for good spaces, you can say TF ring cohomology by space is TF ring cohomology of point, tensor ordinary cohomology by space. But if the action is non-trivial, that's not a ring isomorphism statement. But with a trivial action, it is. So this guy is a polynomial ring of one variable. So this is what we're going to call Z bracket H bar. And that's where the extra H bars be naturally situated. So what I haven't told you yet is how to find cycles in here that are invariant under these operations, under this group action, and give you classes that satisfy this recurrence relation. But that's what we're heading for. To say that that there's natural cycles in the cotangent bundle that satisfy these better this better recurrence relation. And actually the puzzles most naturally want to be computing the product of the structure constants for that basis, not on the Grassmannian. But you can recover the ones on the Grassmannian by taking H bar to infinity. So one thing I will tell you really quickly is what the analog is of the AJS Billy formula for restrictions of these classes. So and I'll tell you this for the corresponding things on the flag variety instead of on the Grassmannian. So it's due to Shangjian Su, and it's called restriction of stable basis. So before, what we need, so what do I want to do? I've got the stable basis element for some Weyl group element, and I want to restrict it to some other Weyl group element. And so we need, as before, as in AJ's Billy, we need to pick a reduced word Q with product V. Now, remember that our original point class was, that one we know, so that's got degree equal to the dimension of G mod B. And that's degree 0, so all these other guys, all of them have the same degree, they're all up in degree dimension of G mod B. So the identity, for example, is not in this basis, not like this guy. So here, down here we were getting the identity, but here we're not. So I'm going to need something that will give me a polynomial of that degree. So extend to Q prime reduced for W naught, the longest element in the Weyl group. So now I want to sum over subwords of Q. And I'm going to, as I'm leaving a blank, I'm going to, as before, take a product over the entire word. So this is the difference. Before there wasn't a Q prime. But I take a product over the entire word, little q running through that. And I'll take a reflection, a multiplication operator if Q is an S. And what you were used to before is to have a reflection operator here, and then we would apply things to 1. So if Q prime were empty, then this would look like AJS Billy. Except I didn't say anything about my subword having the right product yet. Okay, but this thing will have, this formula as written will have various different degrees, and I know I want the degree to be the length of this. So I need another term, h bar minus alpha. That's if Q is not in S. Okay? So either this is here or that's here. This is the weight, going to be the weight of the torus acting on the tangent direction. This is going to be the weight of the torus acting on a cotangent direction. Minus for the co, and h bar because my dilation was acting on the cotangent fibers. And finally, there's a weird thing here. I need to count the number of subwords of S where the product of R is W. So this is some natural number up front. It might be 0. And if it's 0, then maybe I shouldn't have included that in the sum. But here's where the restriction that's analogous to AJS Billy is coming from. So, exercise, take this formula and take h bar to infinity and recover the AJS Billy formula. Questions? Yeah. Also due to Sue with Gufeng Zhu and Sean Lange. Sue has a paper papers now, so you can go through some paper. It's called like one thing that's interesting about it. So the K-theory version of partial alpha doesn't square to 0, it squares to itself. So this guy in cohomology is squaring to 1, and then if you want to do the K-theory version of Malka-Kukov stuff, you should get something that's mixed between squaring to 1 and squaring to itself. It should satisfy the heck algebra relations.
I have a question. Is there something you wanted to show us on the projector?
Just the puzzle pieces. I was going to use this.